Okay, so now it's section 1.5, sum of a series. Before we start going through the complex numbers sum of a series, we're going to remind ourselves of geometric progression formulae, the sum of the series of geometric progression. So obviously geometric progression, you have got the sum of the terms where you are multiplying the previous term by the common ratio to get to the next term. So here A is the first term, R is the common ratio, and you are going to sum n such term. This actually here is the nth term. So here's the formula. I prefer this form. You may have learned it as A in brackets r to the power of n minus 1 over r minus 1. I prefer to use this version though. Then you also remember from the Pure Year 2 chapter Sum to Infinity of Geometric Series is simply A over 1 minus r, provided the ratio is, the common ratio is between minus 1 and 1. If it's between minus 1 and 1, then this series is convergent. Okay. Before we start example 13, I'll show you a useful trick that we'll do a couple of times in the next two examples. So it enables us to use these two identities. So here we go. So the thing to do is, first of all, to note is it works with a complex number plus or minus 1, or 1 minus plus or minus a complex number with a power. So the idea is to make this bracket into z with a power plus another z with a power, and those powers need to be equal in size, magnitude, but opposite signs. It's very, very simple. You've got to multiply the bracket by z with the power that makes this power into half of it, so clearly minus 1. So imagine multiplying it out. You are going to get z to the power of 2 multiplied by z to the power of minus 1. When you add the powers, you get z to the power of 1, and then 1 times z to the power of minus 1. And this one here, clearly it can be replaced with 2 cos theta. So over here, let's just think, what could we multiply this by? It's by half of whatever the z has as a power. So it's got to be a half, but with a minus. So when you then multiply it out, you get z to the power of 1 times z to the power of minus a half. And adding the powers will give you z to the power of a half minus 1 times z to the power of minus a half. Okay, so this one over here is going to be with a minus, so it's 2i, the second identity, sine, almost wrote cos, theta over 2. Okay, now you can have obviously the terms reversed, so over here still the same idea. Let's multiply it by z to the power of half of this power, but with a minus, so minus n over 2, and let's multiply it out. You're going to get z to the power of minus n over 2 minus z to the power of n times z to the power of minus n over 2. So adding 1 plus minus a half n gives you n over 2 as the power. So this one clearly, if you take the minus out, you have z to the power of n over 2 minus z to the power of minus n over 2, which gives you minus 2i sine n theta over 2. Now over here, you need to really be careful. These three work. This one, if you try and do the same trick, so if you try to multiply it by z to the power of, let's choose half of that is 3 over 2 minus 3 over 2. You'll get 2 times z to the power of minus 3 over 2. Add z to the power of 3 times z to the power of minus 3 over 2. That gives you 3 over 2. You can't replace this expression with the identity. You've got 2 of these and you've got only 1 of these. So if you had 2 of each, that could work because you could factorize 2 out, but not of different amounts. So you cannot use the identity here. Okay, so we are moving on to example 13. We've got a complex number z equals to cos pi over n plus I sine pi over n, which can also be expressed as e to the power of I pi over n. We've got to show that the sum of 1 plus z squared plus all the way to z to the power of n minus 1 can be expressed as 1 plus I cot pi over 2n. So this is our focus. We're going to start with the left hand side, which is 1 plus z squared plus all the way to z to the power of n minus 1. So as you can see, to get to the next term, we are multiplying by z. This is a geometric progression, so the sum of geometric series is Sn. We do have n terms. A times 1 minus r to the power of n over 1 minus r. In our case, the first term, a, is equal to 1. The common ratio r is equal to z. So let's substitute, let's replace our series by the sum of the series. So it's going to be 1 minus z to the power of n over 1 minus z. Okay, so here we've got the expression in terms of z. We're going to replace our z. It's a bit tedious to write it in trigonometric form, so we're going to use the exponential form, and that's raised to the power of n, and 1 minus e to the power of I pi over n in the denominator. So the numerator, if you could see, you're multiplying the powers because you raise this to the power twice, n's will cancel. So you're going to have to work out what 1 minus e to the power of I pi is. E to the power of I pi is cos pi plus I sine pi. So you can work it out. Cos pi is minus 1 plus 0 I. So that's minus 1. So coming back to this, you will have 1 minus minus 1, which is equal to 2. So in the numerator, we've got 2. Now in the denominator, what we can do at this moment is, since you've got 1 minus 1 of something to the power, you can actually multiply this by e to half of that power. So we're going to times it by e to the power of I pi over 2n, because if you halve pi over n, you are going to get pi over 2n. So in the fraction, if you multiply the denominator by e to the power I pi over 2n, you must do the same to the numerator. So let's multiply it out. You've seen it 4 times on the previous page. You will have e to the power of I pi over 2n minus, sorry, apologies, we need to multiply it by minus, yeah, of course, otherwise you will have too much here. So minus, and this one here will go to e to the power of I pi over 2n. There you go. So over here we've got 2e to the power minus I pi over 2n. Okay, so in the denominator you have got, if you reverse these, you have e to the power of I pi over 2n minus e to the power minus I pi 2 over n. So we're going to use z minus z to the power minus 1 is equal to 2I sine theta. Identity, theta here is pi over 2n. So, but it's a minus because these terms are reversed, so minus 2I sine pi over 2n. This is what we've got in the denominator. In the numerator, we can express this as in the trigonometric form. Now we've introduced trig form in the denominator, let's do it in the numerator. So this is simply cos minus pi over 2n plus I sine minus pi over 2n. So let's multiply, let's get the minus out of the sign, so incorporate it into the expression. So cos remains positive, and we've got minus I sine pi over 2n. Okay, we're going to divide it by minus 2I sine pi over 2n. So we're going to divide by 2, so it's 1, and this one is minus 1. And now in the denominator we've got I. The idea is to get rid of that I here, so you've got the real number in the denominator. So let's just go on to another page to continue. Okay, if I go down here, you'll be able to see my last line of work. So here we are going to have in the denominator we've got minus I. So if I multiply that minus I by I, we are going to get minus I squared. So it's minus 1. So that's going to give me 1. So that's what I'm going to do, multiply both the numerator and the denominator by I. So in the denominator we are going to have minus I squared, so that will go to 1 sine pi over 2n. And in the numerator you will have I cos pi over 2n, and then again minus I squared sine pi over 2n. So minus I squared will go into positive sign, so I'll put the sign first. Sine 2n plus cos pi over 2n with an I. Okay, now just separate, so let's split these. So sine pi over 2n over sine pi over 2n as your first part. And it's always a good idea to keep on glancing at what you are aiming for. We're aiming for 1 plus I cot pi over 2n. So remember, cot pi over 2n is going to be equal to cos pi over 2n divided by sine pi over 2n. So let's see if we're going to get it. Cos pi over 2n over sine pi over 2n, and it's good news. So because the first fraction clearly divides by 1, and you've got plus I, this simplifies to cot pi over 2n. Okay, and this is example 13 done. Okay, so next stage is, before we begin example 14,